Hello. This presentation is devoted to the aviation meteorology, and especially I would like to introduce a remote sensing tool that helps to monitor the wind regime in the target area, which is the airport. And this tool is called lidar, and it seems to be a useful assistant in increasing safety of the landing and takeoff of the aircraft. My name is Ladislav Gál, and this presentation was prepared together with my colleague Pavel Nechaj. We both are employed by the company MicroStep-MIS, and we both also graduated from the Comenius University in Bratislava. Actually, Pavel is also a PhD student there. The majority of this presentation is a result of the work carried out within a scientific project funded by the Slovak Research and Development Agency in the period 2016 till 2020, and with the title of a Novel Method for Low-Level Wind Shear Alert Calculation from Data Measured by lidar. So what is this presentation about? It will be divided practically into three parts. The first third will be devoted to the low-level wind shear in general and its role in the aviation and the danger that it poses to the aircraft during the phases of landing and takeoff. I will also talk about two accidents which were caused by this dangerous phenomena, and also about the components of the warning system that is aimed at avoiding such accidents. Obviously, the main focus will be set on the lidar technology. The mid part of the presentation will be devoted to a sequence of the lidar and radar snapshots. That was an event that took place during the summer day in July 2018 at the Bratislava airport, and it will be a presentation of a series of gust fronts that appeared within a short period of time. The evolution of these events will be presented by a parallel analysis of the lidar and the radar snapshots. In the end, we will return back to the theory, and we will focus on the estimation of the wind shear alerts along the runways and in their vicinity, and also the way these alerts are transferred to the flight crew. So something about the company. MicroStep-MIS is a Slovakia-based private company which offers complete solutions from observation, data collection to visualization, modeling and forecasting in all kinds of environmental scientific fields, for example, meteorology, climatology, hydrology, oceanology, seismology and air pollution monitoring. Since the year 1993, our company has become a key player worldwide in environmental monitoring equipment, software and hardware supply. This is underpinned by the fact that we have had contracts with national hydrometeorological offices, organizations and companies from more than 75 countries all around the world, and also that we have established a number of local offices worldwide, from China to Australia, from Dubai to Thailand, and so on, also Russia. So let's go to the presentation itself. Wind shear. The wind shear is a change in the wind speed and wind direction, or the change of both attributes of the wind vector simultaneously. It has a key role in aviation. Low-level wind shear was defined by the International Civil Aviation Organization as the wind shear in the lowest 500 meters above the ground level. Sudden changes in wind speed and or wind direction may cause serious disturbances in aerodynamic flight conditions, and therefore wind shear can jeopardize the safe takeoff and landing of the aircraft. In the atmosphere, there are different reasons which can lead to the occurrence of the low-level wind shear. The schematics display some of them. For example, orography can cause differences in the airflow near the mountain ridges and along the valleys. For example, the gust front. The gust front is the divergence out from an intense thunderstorm cell when the cold air flows downwards, and then when it reaches the ground to the edges. In the third example, we mention low-level jet stream. That is a significant amplification of the airflow in the lower troposphere, which is manifested by a local maximum of the vertical wind profile. The next example is the sea breeze. This phenomena occurs due to the differences in the diurnal course of the temperature of larger water bodies and the land surface temperature. And last but not least, I would like to mention, with no illustration, the fifth example. This is the temperature inversion. This means vertical wind shear. This is very typical for our target area. This is the Bratislava airport, and it is often reported by the pilots who encounter different wind regimes below and above the level of inversion. Now, some more details about a very dangerous phenomena that is called microburst. Microburst is an extremely strong downburst in thunderstorm cells with horizontal dimensions up to 4 kilometers and with the following properties: intense downward movements, cold air and high pressure at the ground, intense divergent outflow at the ground, and one or more rotors developed at the edge of this phenomena with significant wind shear. Microbursts may or cannot be accompanied by precipitation, and on the basis of this fact we divide wet or dry microbursts. And also this fact affects the ability of their detection by the radars or lidars. What happens if an aircraft encounters a microburst? Here is a schematic which can be divided into three parts: the headwind, the downburst, and the tailwind part. The green line denotes the ideal trajectory of the airplane with no microburst, and the orange line denotes the trajectory that is affected by the presence of the microburst. So first, when the pilot meets the headwind, the headwind lifts the aircraft above the planned trajectory, and the pilot may observe increased airspeed. Therefore, pilots may reduce the thrust, which may later turn out to be as a mistake, and tries to return back to the original planned trajectory. In the second phase, the downdraft phase, the airplane starts to sink, and again the pilot attempts to regain the original flight path. In the third phase of the movement, the tailwind instantaneously reduces the aircraft's lift and the airspeed. Thus, the airplane still keeps sinking. pilot keeps attempting to return back to the original flight path, but the meteorological circumstances and also the reduced thrust may complicate these attempts, and sometimes these may lead to fatal consequences. And now we arrived to a presentation of two disasters which may be understood as milestones also in the viewpoint of the combination of meteorology, aviation, and flight safety. The Wikipedia's page, which focuses on the accidents in the commercial aircraft, lists, I think, 11 cases between the period 1973 till 2011 where microburst was identified as the most probable reason of the accident, and in these cases total number of fatalities converged to 1,000. And I will mention two of them. The first very important case took place in the year 1975 at the JFK airport in New York. The flight from New Orleans to New York encountered a phenomenon called microburst. So a severe storm broke out near the JFK airport. The air traffic controllers reported that in the locality there are slight showers, nearly zero visibility, strong winds, and extremely strong wind shear. Unfortunately, Eastern Airlines Flight 66 flew into a microburst, and in the final phase of the landing hit the ground and exploded, leaving more than 100 people dead, including 6 crew members. The investigation of the accident later revealed that a series of mistakes was made both by the air traffic controllers and the pilots of the Boeing because even though they had the information about the presence of extreme wind shear in the area, the pilots of the Boeing attempted to land, and this was the most important reason of this fatality. So this accident prompted efforts towards development of a warning system on low-level wind shear, and also meteorologists started to study phenomena like these, and then later these phenomena were termed as microbursts. The second accident, also considered as a milestone, happened 10 years later in the year 1985 at the Dallas-Fort Worth airport. The flight, the Delta Airlines flight 191 on the route from Fort Lauderdale, Florida to Dallas encountered a microburst. The captain was aware of the fact that they were flying into a storm with heavy rain, but he had no information about extreme circumstances related to the wind shear. Even the pilots of the aircraft that landed just in front of them have not reported such extraordinary wind shear conditions. So this flight 191 flew into a microburst, and in the final phase, approximately 300 meters above the ground, the airplane started to descend below the planned glide path from which it never recovered. In the final phase of the landing, the aircraft ran across a farmland at a high speed, across the highway. Its engine hit a car passing by, and the driver of this car was immediately dead. And finally, the plane ended, broke into pieces, exploded, and this accident caused that more than 130 people were left dead. These accidents caused that specialists tried to develop a system that could help avoiding accidents like these. And recently, in the meteorological practice, a complete warning system on low-level wind shear alert consists of 3 subsystems. These are the system of anemometers located near the airport. The second is the meteorological Doppler radar, which is designed to monitor the phenomena in wet atmosphere, for example, fog, precipitation. And the third part of this system is the meteorological lidar, which is aimed at monitoring phenomena in the dry atmosphere. In the next slides, I will present all parts of these subsystems, at least by a couple of sentences. As mentioned, the disasters of the airplanes, mostly the accident of the Eastern Air Flight 66, caused that low-level wind shear alert system was developed. It was initiated by the Federal Administration of Aviation in 1976. This system, LLWAS, consists of several anemometers located near the airport. And the number of anemometers is from 6 to 32, and these are located at a maximum distance of 3 nautical miles from the runway end. The wind shear is determined on the basis of mathematical algorithms based on the data obtained from pairs or triplets of anemometers. The system is still being used worldwide, but we have to say that it has some drawbacks. First of all, the system estimates the wind shear indirectly and only up to the height of 40-50 meters that is defined by the height of the mast towers. Second, the installation of such a system is maybe not straightforward for a number of reasons from the financial, administrative, or technological point of view. The second part of the subsystem is radars. The majority of the airports worldwide are equipped with the radars of the TWER category. That means the terminal Doppler weather radars. As it is illustrated, in the US there are more than 40 of them. The word terminal refers to the fact that they were especially developed for monitoring airflow and wind field near the airports. The advantage of the TWER system over the conventional meteorological radars lies in their finer resolution, finer temporal and spatial resolution. Beyond the precipitation, they also monitor the wind field and the extreme wind shear, not only near the airports, but within the radius of 90 kilometers from them. And now we arrived at the LiDAR technology. LiDAR is an acronym that stands for laser imaging detection and ranging, or light detection and ranging. The LiDAR emits pulses of infrared light into the atmosphere and detects the backscattered light that are reflected from the particles floating in the air. These particles can be of natural or anthropogenic origin, and for example salt and dust, and the wind-induced movement of those particles changes the frequency of the reflected signal. On the basis of the Doppler law, the radial wind speed can be estimated by comparing the frequency of the emitted and the reflected signal. The best conditions for the LiDAR detection are in the misty or hazy atmosphere, since in these cases the concentration of aerosols is ideal, while a very clean atmosphere is not favorable for the lidar detection, because there is a very relatively low concentration of aerosols to reflect the laser signal. On the other hand, a high concentration of aerosols or intense rainfall can cause attenuation of the lidar signals. Now we have two schematics of the lidar. The first one is related to the emission and the detection of the lidar signals. And the second, on the left side, we can see a very important feature of the lidar or also the radar detection, that these remote sensing tools only can detect the projections of the actual wind vector into the direction of the beam. That means the line of sight. So the movements that are perpendicular to the direction of the beam, the lidar or radar cannot detect. So therefore we only can detect the radial components of the actual wind vector by the lidar. Here we have a table, a comparison of the most important similarities and the differences between the lidar and the radar technology. The principle of operation of both tools is similar. However, due to the difference in the electromagnetic waves used, the size and the character of the target objects is different. Practically, we can say that a combined system of meteorological Doppler lidars and Doppler radars can cover the complete spectrum of hydrometeorological phenomena, both from dry and wet atmosphere. So, now we have a couple of pictures from the lidar that is installed at the Bratislava airport. So the lidar of type WindCube 200S from the French manufacturer Leosphere has been in operation at the Bratislava airport since June 2018. It is a block-shaped device weighing over 200 kilograms and with a volume of approximately 1 cubic meters. The maximum horizontal range of this lidar is approximately 6 or 7 kilometers defined by the manufacturer. However, this value significantly depends on the fact on the setting of the parameter of the lidar, as well as on the meteorological circumstances, such as the type and amount of the pollutants in the atmosphere. Now we present a snapshot from the Google Earth software just to illustrate the location of the Bratislava airport in the perspective of the capital city of Slovakia. The airport lies in the eastern outskirts of Bratislava, approximately 9 kilometers away from the city center, and at the altitudes of 112 meters above the sea level. The lidar is located near the cross, near the junction of the two runways, at a distance of approximately 250-300 meters from the axis of the runways. It is important to note that the overall wind regime in Bratislava and especially at the Bratislava airport is highly influenced by the Little Carpathians mountain range extending from Bratislava in a southwestern to northeastern direction. The meteorological radar of the Slovak Hydrometeorological Institute is also installed at one of the hills of the Little Carpathians at the altitude of approximately 600 meters and in a horizontal distance of 10.2 kilometers from the lidar located at the airport. The lidar at the airport predominantly works in the so-called PPI regime. That means plane position indicator, where the optics of the device is set to a constant elevation while it is rotating continuously from 0 to 360 degrees. The constant elevation is set to the value of 3 degrees, which corresponds to the slope of the glide path of the landing aircraft. According to our settings, a narrow sector of a width of 3 degrees is scanned for 1 second, so a complete PPI scan is achieved exactly in 120 seconds, that means 2 minutes. The results of a PPI scan is a cone surface, which is then displayed, which is then projected into a two-dimensional plane as a circle with a lidar in its center. Unfortunately, we have two invisible sectors in Bratislava which are invisible for the lidar beams emitted under the 3 degrees elevation, and these are caused by the buildings of the fire station and the building and the tower of the meteorological observatory in Bratislava. And it is also visible at each lidar snapshot. Some more information to the lidar snapshots. It is important to note that in these snapshots we have some important reference points, and first of all, this is the lidar itself in the center. Then this purple magenta crosses the name of each runway, and then we have a number of further crosses denoting the distances of 1, 2, and 3 nautical miles from the runway ends. And also the inserted table is related to these reference points, and these denote the height of the lidar beam above the ground and also the distance of this lidar beam from the lidar at each reference point. And we can see, generally we can say that the lidar beams reach approximately 350-400 meters above the ground in a distance of 6-7 kilometers away from the lidar, and this is approximately the volume which can be reliably scanned by the lidar. The convention says that the wind speeds are denoted as positive when the wind blows towards the lidar. So in this illustrative example we have light wind blowing towards the lidar from northeastern direction, and with a maximum radial wind speed of 3 meters per second. Now we arrived at the second part of the presentation, and now I would like to show a series of snapshots illustrating an evolution of an interesting weather event that took place on 5th of July 2018, where a series of gust fronts appeared at the Bratislava airport, and these events were parallelly detected by the meteorological lidar and the meteorological radar. The air in the target area, or generally in Slovakia and Central Europe, was on that day warm and moist, with cold fronts approaching from west towards Slovakia. The initial situation is at 3:30. The wind field in the target area is relatively stable. The wind blowing from the direction of 160 degrees, that means southeast, and with a maximum radial wind speed of 9 meters per second. And neither the wind direction and the wind speed changes with altitude. But if we look at the same time on the radar snapshot from the Slovak Hydrometeorological Institute, and using the product of CAPI, 1.5 kilometers, we can see that something is developing in the southwestern direction from the runway 4, approximately 15 kilometers from this point. Thunderstorm cell is being developed, and a couple of minutes later we will see the effect of this thunderstorm also in the lidar snapshot. We can go further on the sequence of these snapshots, and slowly we approach the situation where in the southwestern corner of the lidar snapshot, radial wind speed starts to increase. The thunderstorm cell is slowly approaching the runway 04. This is in the southwestern direction, and the gust front from this thunderstorm cell, which is the divergent outflow from the thunderstorm, slowly reaches the position of the lidar. Here at this timestamp of 2 p.m. 56, 4 minutes before 3, the gust front reaches the lidar, and we can see at this position, at this time, that the wind field has been completely rearranged. Now the wind blows from the southwestern direction and with a maximum radial wind speed 50 meters per second. We can also reveal that this situation remains stable for the next approximately 20 minutes. As the time goes by, the thunderstorm cell in the southwest slowly weakens, but we can see that something new is being developed on northeast and at the opposite side of the airport, and as we click on the farther snapshots, we can see the weakening of the thunderstorms in the southwestern direction and strengthening the series of thunderstorm cells in the opposite directions. The footprints of these storms in the north and northwest also appears in the northern parts, northeastern parts of the lidar snapshot, changing the color, and we can see on the next lidar snapshot that this gust front, again, the divergent outflow from this thunderstorm cell, is rapidly moving towards the lidar, and this situation is very interesting. At the timestamp 3:40, the wind blows towards the lidar from approximately 2 opposite directions, and the first is related obviously to the movement of the gust front from the northeastern direction, and on the opposite side there is the prevailing wind flow in the area that is from the direction of the southwest. We can see that in this position the front side of the gust front got at the other side of the ladder, but on the other side new thunderstorm cells are developing in the west and in the western parts and the northwestern parts. The second gust front slowly disappears from the area of the airport, and again a new stable wind field was formed. The new wind field is characterized by winds from the northeastern direction and with maximum radial wind speed of 30 meters per second. And this situation remains stable for a couple of minutes, because another gust front, the third one, comes very quickly from the northern direction, and we can see here the intense colors, purple colors, indicate the appearance of very strong winds in the area. And here in these positions, in this time, we can observe the maximum radial wind speeds during the whole event, reaching approximately 90 meters per second in this area. And as the situation goes further, the thunderstorm moves. The area is also affected by the precipitation that is brought into this area by these systems, and this is illustrated by the fact that lidar signals slowly are attenuated. The lidar signal weakens and can detect narrower and narrower areas in this time, 4:30. As the situation goes further, lidar signals are lost for a couple of minutes practically due to the intense rainfall, and a couple of minutes later again the lidar signals, the area covered by the lidar signals widen. The wind calms down as the thunderstorm crosses over the area of the airport, and finally, as it is illustrated by the radar picture, the thunderstorm leaves the area of the airport, and the lidar signal again widens. So this was the presentation of this situation where a series of 3 gust fronts appeared in this area, and now I would like to turn again to some theoretical information in the last third of the presentation, and these theoretical information are related to the detection of the wind shear alerts in the area of the airport, and some technical aspects, the definition of the wind shear alert, and so on. The general recommendations for the detection of the wind shear originate from the International Civil Aviation Organization, from the low-level wind shear alert system. The wind shear should be reported within an imaginary box that is called arena. Areas noted for attention, and this has the following dimensions: 3 nautical miles from the runway end on the arrival corridor, 2 nautical miles from the runway at the departure corridor, half a nautical miles at either side of the runway along the center line of the runway, and 160 feet, that means approximately 500 meters in height. And the wind shear alerts are issued to the pilots in the cases when the headwind loss or gain along the flight path of maximum 4 kilometers exceeds 15 knots, that means 7.5 meters per second. There is another category for issuing wind shear alerts for stronger wind shear alert that is called microburst alert, and microburst alerts are issued when the headwind gain or loss also along this flight path of 4 kilometers exceeds 30 knots, that means 15 meters per second. These alerts are then delivered towards the pilots and the air traffic controllers also via the system called WSP, Weather System Processor. Here is an example of a short message decoded by this WSP system, and also a schematic of the orientation of the runway, also the imaginary box of called arena from above, and also the position of a hypothetical microburst indicated by the orange circle, and with the wind speed reaching within 35 knots. The runway is denoted by purple color. The pilot should obtain a message like this, indicated in bold, and this should be translated as follows. 27A means that on the approach corridor towards the runway 27, there is a microburst alert issued, MBA. 35K minus means that the pilot should anticipate 35 knots loss of airspeed, and the abbreviation of 2MF refers to the position of the first encounter with this phenomena. That means 2 miles out on final approach. The remaining two figures, 250 and 20, refer to the properties of the wind down along the runway 27, 250, that is the direction of the wind in degrees, and 20, this is the wind speed in knots. We have implemented the recommendations of the ICAO into our algorithms, but we also extended them in two ways. First, we do not focus explicitly on the boxes defined by arena. We look at each lidar being instead. For the second, we do not use the precision of 1 nautical miles that comes from the definition of the arena, but we use the precision to identify the exact location of the wind shear alerts that originate from the range gate resolution of the lidar, that is 100 meters. So I would like to just to present two examples of the wind shear alert analysis. We have the first situation has already been shown. This is a situation when the wind blows towards the lidar from approximately two opposite directions. From the northeast, due to the movement of the second gust front, and from the southwestern direction due to the prevailing wind flow in the area. And we can see the sector denoted in the northeast, denoted by pink circles, either solid circles or empty circles. They indicate the position of the wind shear alerts or microburst alerts. We can see that a relatively wide sector in the northeastern direction is covered by wind shear alerts, and along the near the runway 22, a narrow sector is covered with stronger alerts, the microburst alerts, and the maximum wind shear reaches 22 meters per second in the direction of 33 degrees. The second example comes from the time 12 minutes later, when the front side of the gust front southwest from the lidar. The situation is similar because a very wide area is covered by the points, by the pink circles denoting wind shear alerts, and also there is a narrower area with the microburst alerts close to the runway 04. The largest wind shear reaches to 20 meters per second in the azimuthal direction 225. So, as the lidar technology became available more generally, there appeared a number of other interesting topics that got focused attention in aviation. So I would just like to mention some of them. For instance, one very interesting topic is the glide path scan, because it is more sophisticated method to get the information about the headwind profile along the glide path of the landing aircraft, and instead of a full PPI scan, the lidar is set to a scanning where narrower azimuthal areas are scanned, also with under slightly different elevations, just to cover the corridor of the landing glide path, and just to get as precise information about the headwind profile as possible. I can say that our company is also working on this topic. We are now developing and trying to implement this methodology into our practice. Another important and interesting topic is the analysis of the wake vortices. Wake vortices are turbulent waves that appear behind the engines of large aircrafts, and may be very dangerous for smaller aircraft if they got very close in their vicinity. The wake vortices, the studies of wake vortices may help, for example, in optimization of the airport throughput and, for example, to reduce delays. Another interesting topic is the turbulence monitoring using the lidar technology. For instance, during the summer thermal convection, lidar can scan the target area very in details and can help to derive very detailed characteristics of the boundary layer. And last but not least, I would like to mention the possibility to detect the overall long time regime of the wind in the target area, and using the lidar technology one can get a very detailed windrows. Now we arrived at the very end of my presentation, and let me just summarize what I have talked about during the previous, for example, hour. I have just tried to show that the lidar technology is has plenty of advantages. The lidar is able to monitor the evolution of meteorological phenomena and the wind field in a very high spatial and temporal resolution. For the second, the Doppler radar and the Doppler lidar can complement each other's weaknesses and strength. The analysis of the wind shear alerts is also possible on the basis of the data obtained from the lidar. And so the analysis and issuing wind shear alerts according to the recommendations of the International Civil Aviation Organization. LiDAR is very good at detecting meteorological phenomena that are seemingly invisible for the for meteorologists and for the pilots, and this is an example of dry microburst or the vertical wind shear, when the pilots landing in Bratislava often complain about the different conditions due to the different wind regime above and below the level of the inversion.
I can say that the presented system, the presented lidar system of our company, MicroStep-MIS, is now in the testing phase. It is being tested and will be available for the civil aviation right after the certification from the Slovak Transport Authority will be available. For those who are interested in the topic and would like to read up a little bit more, I would like to recommend our scientific paper that was published at the end of the year 2019 in the International Journal of Environmental Research and Public Health, and we published also this, the core of our presentation is there, but also illustrated with some more examples, snapshots, lidar snapshots, and radar observations. This is all from my side. We reached the end of my presentation. I hope you enjoyed it, and I thank you for your attention.